Hello everybody! This time I would create another 2D post-processing filter that could be useful if, for example, we want to display a newspaper article with a color image in our game, which should look like it was printed on an inkjet printer. In other words, we'll convert the image into a 4-color raster in CMYK coding. Let's get started. What is halftoning? It's a technique for simulating any color using a combination of primary colors arranged in a pattern, which the human eye perceives as a result of mixing these colors. As I mentioned at the beginning, it is used in inkjet printers, for example, and if we enlarge a printed paper with an image from such a printer using a magnifying glass or a microscope, we can see a pattern of dots that form the final image. We can find plenty of information in a detailed Wikipedia article. This time, we'll be working with an image, so I'll create a scene containing the usual background from our game. Let's do it. I right-click on the scenes, create new scene. Let's call it, I don't know, halftone, sure. Okay, and as I said, we'll use a picture. So we have this screenshot right here. I'll drag it to the scene. It created the sprite 2D node automatically, and let's improve the parameters. So the translation position should be reset to 0, 0, and in offset, let's cancel centered. Now it fills the viewport perfectly. Okay, and of course we need to create a new shader material. So here I will expand material, new shader material, click, and new shader, which is called halftone GD shader. It's canvas item. I'll just put it to the shaders folder here. Okay, and create, and click again to open it in the editor. Let's expand it editor a bit. Alright, and as usual, I will delete the stuff we don't need, vertex and light, done. So, as I mentioned, we'll be working with the CMYK color model, which has 4 color components: cyan, magenta, yellow and black. However, the texture function we use for reading pixels returns color in the RGB format, so we'll need to start with a conversion function. The code I'm about to write is based on a well-known formula that I've simply translated into shading language. The function looks like this. It will return back 4 RGB to CMYK, and the parameter is vector 3 color in the RGB format. And let's start with defining K, the black color, 1 minus max color R and max color G, color B. Okay, and return the vector 4 with these components. First would be 1 minus color R minus K divided by 1 minus K, and we'll use a very similar calculation for other components, so it would be G and B. Okay, and the last one is simply K and semicolon. Okay, is it correct? R? No, of course not. R, G, B. Sorry. G, yeah. B. This is correct. Great. Now that we can convert the color to the desired format, we'll want to render a grid of color dots for each of these 4 color components. To achieve this, I'll write a function called grid. But before we dive into that, let's define 2 uniform parameters that we'll need for properly rendering the grid. These are density, to set the density of the dots, and intensity for the brightness of each color component. Since the intensity will be different for each color, we'll create it as a vector 4, while density can be a float. Let's do it. Uniform float density with a hint range and initial value 100, and the hint range can go from 1 to, let's try 500 for a really dense grid of dots. And now the intensity, so uniform, as I said, vector 4 intensity is vector 4 initial value 0.8, 0.9, 0.8 and 0.6. Okay, again a result of my experiments, and we can then adjust these values in the inspector to fit the desired intensity of all color components. Very well, and now the grid function. It will have 3 input parameters: the UV coordinates of the current pixel, the grid rotation angle, and the image resolution to calculate the aspect ratio. I'll write the function first, then explain what we need these parameters for. I'll do it here after the first function. Okay, so it would be vector 2 grid, 2-dimensional grid we want to generate, and input parameters, as I said, UV coordinates, the angle, and resolution, which will calculate from the dimensions of our texture. And now the calculation float aspect ratio is resolution X divided by resolution Y. You may remember that from our previous videos where we used exactly this formula to calculate the aspect ratio for the color act. So this is nothing new, and now let's return the actual grid. Return vector 2 with the following components. We'll use modulo to get some repetition of the dots. UV X multiplied by aspect ratio. This is important. If we don't do that, the grid would be stretched horizontally. So we want it to display it always the same way, regardless of the texture dimensions. And now the pattern. So it would be multiplied by cosine of the angle. This is basically taken from the formula for the 2-dimensional rotation, and minus uv dot y multiplied by sine angle. Okay, 1, 2, and we must what? Multiply that by the density, of course. Density. And the fourth and the second parameter is 1. I mean, this is the parameter for the modulo function, and a very similar calculation for the y coordinate. So it would be, this is the same, and now we have sine here. Okay, minus, no, not minus, but plus. It is all taken from the rotation matrix we've been using in some previous videos. And okay, sine, and this is cosine angle, density 1, and dot, and let's get rid of this comma. All right, seems to be okay. So there is nothing special about the UV coordinates here. We use them almost everywhere, but why the angle? As we can read on Wikipedia, having the grids of all 4 color components oriented the same way would lead to plenty of visual artifacts and moire effects, which we definitely want to avoid. This problem can be solved, or at least reduced, by using a rotation, setting a different angle for each color. I found the optimal angle values somewhere, and I'll use them as a constant vector. in our shader. So let's put it right after info parameters. Const vector 4 angles is vector 4 with these values 0.261, 1.309, 0, no rotation, and for black it would be 0.785. Okay, and as I said, the aspect ratio, the third parameter, resolution aspect ratio, ensures that the grid will always be square regardless of the image dimensions. We'll determine the resolution vector in the fragment function and pass it to this function as the third parameter. Let's do it now. So here we will have the usual start vector UV is UV, and now the resolution vector resolution is simply inverse value of the texture pixel size internal variable, and we will take the current pixel in the RGB format. RGB is texture of texture and UV coordinates, and of course this is vector 4, so RGB to reduce it to vector 3. And to convert it to CMYK, let's define the vector 4 CMYK, which is a result of RGB to CMYK with the argument RGB. Alright, and finally we need to assign something to the color. Let's start with simply using the original pixel in RGB format and 1 for alpha value. Okay, nothing should be changed. Very well. By the way, what would happen if we assign the CMYK vector to the color variable? Let's give it a try. CMYK, and wait for it. Okay, the result is undoubtedly interesting, but definitely not what we wanted to achieve. So we'll revert to the original RGB color. Let me just revert. Okay, and start creating the dot grids. Since CMYK involves subtractive color mixing, we'll begin with white and gradually subtract each component. We'll do this in a loop so that we don't have to repeat the same code 4 times. So we need to do it right here. Vector 3, result, where we'll accumulate the resulting color. Or it won't be a real accumulation this time because we'll be subtracting, but you know what I mean. And now the cycle for integer I from 0 to 4, as we have 4 components. And let's do something. And finally we will use a result instead of RGB, so everything should turn to white now. Very well. Now we need to implement this loop. We'll start by getting the value from the grid function for the current color component, which is determined by the index I, this one. 0 means cyan, 1 is magenta, and so on. So it would be vector 2 grid is the result of the function grid with parameters UV, now angles I, and our calculated resolution. Okay, now we want to get the brightness of this color. We do this by multiplying the corresponding component of the CMYK vector by the set intensity and then dividing the result by the distance of the pixel from the center of the image to get the dot grid. Note that we can also access vector components dynamically using an index, not just with XYZ, W or RGBA suffixes like we did right here. So let's do it. Float value would be, as I said, CMYK and the I component multiplied by the intensity, which is also vector, so it's ith component, divided by the distance, so it's length of grid minus 0.5, because this time we didn't move the origin to the center, it's still at the top left corner, so the center is 0.5, 0.5. Okay, and now we'll need another constant to help us with the final calculation and subtracting. It will be 4x4 matrix with predefined vectors. Let me do that. So const mat4, let's call it vectors, is mat4, and matrix is in Godot shading language composed of vectors, so we need to define 4 vectors. Vector 4, 1, 0, I mean 0, 0, and I'll copy paste 3 times and just change the values. 0, 1, 0, 1, and this one would be like that. And let's get rid of the comma. Okay, and let's use it in the loop. Where is it? Here. So we need vector 3, let's call it component, as it is a color component which will create the particular dot value from the vectors matrix, and it's only its x, y, z components, because well, when we define a matrix 4x4 we must work with vectors 4, but we need only vector 3, so the zeros are basically ignored and we filter them out using this technique, and multiplied by clamp. I will explain that shortly. Pow value to the power of 5 and 0, 1. Clamp the clamp parameters. So as you can see, I made some additional adjustments to highlight the dots which are not visible yet but will be very soon. I raised the resulting value to the power of 5 and then clamped the result to the range from 0 to 1. When I multiply this number by the vector, I get a vector that we subtract from the original white color at the end of the loop. I mean, we only need to subtract the vector with this component and have the rest as zeros. That's why we multiply that with this vector from this matrix. Then we need to subtract this component, then this one, and from the black one we use all 3 for the shades of gray. Okay, and finally, as I said, we'll be subtracting, so the result is we subtract the component from the result. Alright, and we have something already. Let's show the whole picture. Here it is. We can admire the result. If we zoom in on the image, we can observe the typical pattern caused by the rotations of the individual color components. If we like, we can play with the intensity settings to either highlight or suppress certain colors. Let's find them here in the shader parameters, and let's, for example, try this. Yeah, the magenta is more intensive. Yeah, definitely there is something going on there. Let's revert. And density, as we can see, the original value is probably the best. Okay. Thank you for watching. As a next step, we could enhance this by converting additional constants to uniform parameters, such as the exponent of the pow function, which is set to 5, or even the rotation angles of the individual colors. Besides CMYK, there are other color models with which we could do similar tricks, but that would likely require a different approach beyond the scope of this video. So for now, take care, good luck with your projects, and I'll see you in the next video.